Our brains are just wired to see patterns. It's what we do. We find faces in clouds. We see trends in the stock market. We're constantly connecting the dots. But in a world that is just drowning in data, that superpower, well, it can actually be a bit of a problem. So how do we become data detectives? How do we learn to tell the difference between a real clue and just random noise? And that is the central mystery, right? I mean, imagine you're looking at sales figures or results from a medical trial, or even just the weights of dogs at a dog show. You see differences between the groups, for sure. But are those differences actually meaningful? Or could you have gotten the same result just by, pure random luck? That's the question we're going to dig into today. So, our investigation starts with a pretty classic scenario. We have some clear suspects. We've already divided our data into a few groups, and we just want to know if these groups are genuinely different from each other. And the good news is, we're not just relying on gut feelings here. Statisticians have developed a whole toolkit of really powerful methods to put these differences to the test. These tools let us say with some real confidence whether a pattern is a significant discovery or if it's just a statistical ghost. Okay, so let's bring in our first major tool, and we're going to use a fantastic case study to see how it works. A dog show, right? We've got a whole bunch of dogs, tons of data about them, and we'll start with their weight. Our goal here is to explain why there's so much variation in their weights. The perfect tool for this job is called analysis of variance, or ANOVA for short. Now, the core idea behind ANOVA is actually really, really clever. It doesn't just look at the average weight of each group. Nope. It compares two things: how different the groups are from each other versus how much individual variation exists inside each one of those groups. And this slide shows you exactly what I mean. Take a look at the left. If we group the dogs by young versus old, we hit a wall. A young St. Bernard and a young Chihuahua are in the same group, but their weights are worlds apart. So you get this huge variation within the group, and the group averages themselves aren't all that different. It's just not a good explanation. But now look at the right. When we group by breed, something amazing happens. The variation within each breed is pretty small, but the variation between the average weights of a Chihuahua, a Pointer, and a St. Bernard is enormous. Now that is a good explanation. And this is what makes ANOVA so powerful. It takes that gut feeling we all get when we look at that chart on the right, that feeling of, yep, breed is definitely the important thing here, and it gives it a formal mathematical backbone to prove it. So when you boil it all down, it comes to this. ANOVA gives us a big thumbs up when the signal, that's the variation between the groups, is way, way louder than the noise, the random variation within the groups. It's all about that ratio of signal to noise. Okay, that's all well and good for when we already have our groups, when our suspects are all lined up. But what happens when we arrive at the crime scene and we have no idea who the suspects even are? What if the groups themselves are the mystery? Yeah, this is a much tougher case for a data detective. You don't have these nice, neat labels like breed or treatment A. All you've got is this massive, unlabeled cloud of data. I mean, where do you even begin to find patterns in that? And this is the exact challenge we're talking about. This is where a whole different set of tools has to come into play. We need something that can look at this raw data and automatically find potential groups or clusters, just based on how similar the data points are to each other. This whole process is called clustering. It's a type of unsupervised learning, which is really just a fancy way of saying we're not telling the algorithm the answers ahead of time. We just let it loose on the data and basically say, go find the conspiracies. Find the natural groupings where the members are all alike, but are different from the members of the other groups. All right, so this brings us to the climax of our investigation. Our clustering algorithm has done its job. It's found some potential groups, some conspiracies hiding in the data. But here is the million-dollar question. Are they real? And this is such a critical step. An algorithm can always find patterns, even in data that's completely random. So how do we know the clusters it found aren't just a statistical mirage? How do we know this conspiracy is real and we're not just on a wild goose chase? We have to stress test our results. And the gold standard for doing this is a really powerful technique called bootstrapping. Think of it like running our investigation over and over again on slightly different versions of the evidence, just to see if we keep getting the same result. The way we sample the data is what makes this work. We do it with replacement. So imagine putting all of our data points into a hat. We pull one out, we write it down, and then, this is the key, we put it back in before we pull the next one. This means some data points might get picked multiple times, and some might not get picked at all. After doing this to create hundreds of new data sets, we run our clustering algorithm on every single one. Then for the final step, we compare all the results. Are the same groups popping up over and over again? That's what we need to find out. And to compare them, we need a score. That score is usually the Jacquard index. It's just a simple, elegant way to measure how similar two different sets of clusters are. A score of 1 means you found the exact same groups. A score near 0 means the results were totally different. If your clusters are real, they're going to have a high Jacquard score across most of those bootstrap samples. That tells you they're stable. So there are two main ways to do this stress test. Think of Scheme 1 as a loyalty test. It asks, how often do our new data sets agree with the very first result we found? It's all about building confidence in that primary finding. Scheme 2, though, is more like a full-blown investigation. It compares every single result to every other result. It's trying to find the most consistent pattern overall, asking what is the most stable, most reliable story this data is trying to tell us, no matter what we happen to find first. Okay, so after this whole investigation, we've put together a pretty powerful toolkit for any data detective out there who's just trying to make sense of the world. Let's do a quick recap of what we've got. Let's put it all together. When your suspects are already lined up, you use ANOVA. When you have no suspects and you need to find them in a crowd, you use clustering. And, this is so important, to make sure the groups you found are real and not just a fluke, you use bootstrapping to test for stability. These 3 tools are your absolute best weapons for separating that true signal from all the distracting noise. And this, right here, is the real takeaway. The next time you see a news headline or a marketing claim or a scientific study that says, we found a difference between groups, you are now equipped with the questions of a true data detective. Don't just ask what they found, ask them how they validated it. Was it just a pattern or was it a stable, significant signal? That's how you separate fact from fiction.